Hey guys, I just wanted to make you a quick limiting reagents video so you understand the last part of chapter 12. If you can see here, I am on slide 51, and on slide 51 I have put pictures that I took from your notes. If you are wondering, sorry about that. If you are wondering where all of your notes are, they are still on Canvas files, unfiled, and this is chapter 12. So if you're wondering where I got these purple pictures from, that's where they are located. Now what we're going to talk about today is something called limiting reagents. And now I need to get my slides back in order and go to this. So there we go. Now it won't move anymore. Okay, so something we're going to talk about today, it's called limiting reagents. And limiting reagents is, let's use light pink. Limiting reagents is kind of like cooking. I actually have an example on here that we're going to kind of go through before we define what a limiting reagent is. So it says on here, it says let's make BLTs. Now I like BLTs. BLTs, if you're not familiar, are bacon, lettuce, and tomato sandwiches. So I really like BLTs, and BLTs, like just to make one BLT. Now this isn't going to be the best BLT, but it'll just be a BLT. So in other words, to make one bacon, lettuce, and tomato sandwich, I wrote it out as like a chemical equation so you could kind of relate these right here to limiting reagents later. That's my goal here. So to make one BLT sandwich, I need 2 slices of bread. That's this right here. I need 1 leaf of lettuce. That's LL. I need 1 slice of tomato, because anything more than that's too much. And for my BLT, I'm going to put 3 pieces of bacon on it, and that yields 1 BLT. So if you look at that, I'm going to erase all these lines that I drew so we can stay neat and clean with our work. If you look at this, I wrote it like a chemical equation so that you can see this is how I make 1 BLT. Now, what if I wanted to make 2 BLTs? Like, let's say I was going to eat one and my mom was going to eat one. So if I wanted to make 2 BLT sandwiches, all I do is I double my ingredients. So I need 4 slices of bread, 2 leaves of lettuce, 2 slices of tomato, and 6 pieces of bacon to get 2 BLT sandwiches. Now, why don't you guys take a second and look at my third example down, and can you tell how many BLTs I can make here? I'll give you just 1 second. See if you can figure out how many BLT sandwiches I can make if these are my ingredients. Okay, so I'm hoping you said you can make 5 of them, Mrs. Donnell, because if you look here, I have 10 slices of bread, but I need 2 to make 1 sandwich. I have 5 pieces of lettuce, but I need 1, so I can make 5 still. Okay, so 5 BLTs, and I've just taken my ingredients and multiplied them by 5. Now, look at the very last example really quick. This one's a little tricky. How many BLTs can I make? I'm going to give you a good 2 minutes to see if you can figure this out. How many can I make there? Okay, so let's look at our ingredients. Let's say I wanted to make BLTs for the whole classroom right here. And I went to my refrigerator and my pantry, and these are all the ingredients I had in my pantry and my refrigerator. So if I look here, if I have 50 slices of bread, I can make 25 BLTs from that 50 slices of bread. From the 70 leaves of lettuce, I only need 1, so I could actually make 70 sandwiches from that ingredient. 4 slices of tomato, I only have 10. Like, let's say I only have 1 tomato total. I can make 10 sandwiches. But my 18 bacon right here, if I look at that, I need 3 for each sandwich, so I can only make 6 BLTs here. So my question to you from the get-go was, how many total sandwiches can I make? Can I make 25 total sandwiches, or 70, or 10, or 6? I hope most of you are saying, Mrs. Donnell, you can only make 6 total sandwiches because bacon is limiting my production of BLTs. In other words, I only have enough bacon, and after I make 6 sandwiches, I don't have any more bacon to make BLTs. So if I look up here, I would just have lettuce and tomato sandwiches, and that is no good at all. So that kind of happens in chemistry quite often, where you have a chemical equation, like maybe this one where you're making, it doesn't even matter what chemical you're making, but you have a chemical equation and you have varying ingredients up here, varying amounts of your ingredients, and how much product can you actually make? Well, the thing that limits your production is referred to as the limiting reagent. If you look here, the limiting reagent is the reactant that limits the amount of product you can actually make. So in BLTs, the limiting reagent was bacon, because that limited the production of BLTs. Now, this happens in chemistry quite often, and something else that I want to make sure I say before we scroll past this is the limiting reagent is always completely used up. So if you look back up here at this example, my bacon would have been completely used up in this example, and I would have had leftover tomato, I would have had leftover lettuce, I would have had leftover bread, but my bacon is completely used up. The limiting reagent is always completely used up during a chemical reaction, and it limits the amount of product you can make. So, there is some good news, because I have a problem here. The good news is this is just the same thing we have been doing, but with just a tiny twist. So guess what? Thank you for saying what. This is more stoichiometry problems. So we're not getting away from stoichiometry. It's just that with this problem right here, you're given 2 amounts of reactants, and you are trying to figure out how much product you can make. So if you look at this chemical equation, it says I have 6.70 moles of Na, and how much Cl do I have? 3.20? I have 3.20 moles of Cl, and it's saying how much NaCl can I make. So these are just basic mole, well, this one is a basic mole-to-mole stoichiometry problem, but you have to do 2 problems because you have 2 givens. It says here, what is the limiting reagent? So let's go ahead and do the 2 problems. Once again, I was just following steps. I read the problem. I single underlined what I am trying to find. I underlined both numbers one time because I have to do 2 problems. And then I double underlined the product that I'm trying to find. So for this problem, I'm going to go 6.70 moles of Na, and thankfully it is already in moles. So if it's given in moles, I can use my mole ratio to go to the unknown. Now remember, your mole ratio comes from the coefficients in the balanced chemical equation. So I want moles of Na down here and moles of NaCl up here. I look at my balanced chemical equation and notice that the coefficients are 2 and 2. And it says how many moles up, so I'm in moles, I can be done. So 6.72 times 2 divided by 2. If you're fast at math, you already know that this answer is 6.70 moles of NaCl. Units that canceled out here were here and here, leaving us with moles of NaCl, which that's our double underline thing, so we're good to go there. Now, as I mentioned before, we have to do 2 problems. So now we need to do one with 3.20 moles of Cl2. So we're going to go 3.20 moles of Cl2. And we're in moles, so we can use our mole ratio. We don't even have to use a mole map on this one. So we look at our balanced chemical equation, and we say, okay, 1 here, so 1 mole of Cl2 for every 2 moles of NaCl. Okay, units that cancel out here are here and here. Okay, so let's do some math. We have 3.2 times 2 is 6.40 moles of NaCl. Now, if we look back here, when we were making BLTs, if you look at this line right here, we could make 25, 70, 10, or 6. We have to pick the smallest answer. You can't pick the biggest answer. You have to pick the smallest answer. So let's apply that over here. Can we make 6.70 moles of NaCl or 6.4 moles of NaCl? Pick the smaller answer. The end. This is your answer. Now, the other question in this problem is, what is the limiting reagent? Okay, so look here. It's really easy. Look at the smaller answer. Go back to the beginning. Whatever you started with is your limiting reagent. So right there's your limiting reagent. Boom, done. Cl is the limiting reagent. Cl is limiting the production of NaCl in this example. So again, with these problems, you're going to do 2 problems with the things that you underlined one time, and then you're going to pick the smaller answer, and then go back to the beginning, and that gives you your limiting reagent. Done. So these are just basic stoichiometry problems, but we have two numbers given in the problem, but still only one answer. So we're not doing anything differently. We're just doing two problems and saying, okay, we can make the smaller of the two amounts because something is limiting how much we can actually make. Now, one more little itty bitty thing I want to teach you guys before this chapter is over. It's something called percent yield. I gave you the formula for percent yield right here. The percent yield is the actual yield over the theoretical yield times 100. And that just leaves what on earth is theoretical yield and actual yield. Theoretical yield is the amount you get from doing stoichiometry problems. So in other words, the theoretical yield is how much you get from doing math on paper. In other words, from doing stoichiometry. Now, the actual yield is the amount of product actually received when the experiment is carried out. Sometimes it's referred to as the experimental value, but it is always given in the problem. For example, I have one more problem over here. I actually called it one more problem. There, I'll make that into a face for you. Okay, so if we look here, we're going to read the problem first. It says calcium carbonate decomposes to form CaO and CO2. That's right here. So there's your balanced chemical equation. What is the theoretical yield? In other words, how much can I get from doing math on paper? How much can I get from doing the math on the paper of CaO if I start with 24.8 grams of CaCO3? It says, what is the percent yield if, here is my actual yield. It says, what is the percent yield if 13.1 grams of CaO is produced, like produced in lab? So that's your actual yield, and we have to figure out the theoretical yield. This is just a basic stoichiometry problem. So what is the theoretical yield of CaO if there's my single underline, and we'll deal with this in a minute. So I'm going to go 24.8 grams of CaCO3. I have to go from grams to moles. I'm just doing a stoichiometry problem. And I'm saying, how much of this can I make? Like in theory, obviously theoretical yield, in theory, I should be able to make this much. Okay, so grams to moles. So using the mole math, I know there is 1 mole of CaCO3. And then I have to figure out, pretty sure, oh, look at that. Right there, periodic table. So I have to add up the molar mass of CaCO3. So hang on, what was it? CaCO3. Okay, so Ca is right there. So 40.0 C plus 12 plus oxygen is 16, but I have 3 of them, so I get a cool 100. So it's about 100 grams. 100 grams of CaCO3. Grams cancels out. Now I'm in moles, so I can do my mole ratio. So I know this has to go on the bottom, so it cancels. I'm trying to find moles of CaO on top, because that is what I am looking for. So moles, and then look at my balanced chemical equation. Well, wait, is this balanced? Yes, it sure is. Okay, so it's 1 and 1. So this cancels. Now I'm in moles of CaO, so now I need to convert to grams. So in 1 mole of CaO, there are, let's go back down here and add it up again. So 40 plus 16 is 56. So 56 grams. 56 grams of CaO. Now I need to cancel out my units, and I'm in grams of CaO. So let's see what my answer is going to be. Equals. Okay, so I'm going to multiply everything on the top, which is 24.8 times 56, which is 1388.8 divided by 100. Okay, so divided by 100 is 13.888 grams of CaO. Now, significant figure says I can only keep 3 because the number I started with over here only has 3. So I'm going to round that to 13.9 gram. Oh no, what the heck? Oh. Okay, everybody cross your fingers and see if this comes back up pretty quick. Pause for a second, I was so close. Okay, slide 51, let's see if we can get back in. Probably have to wait just 1 second for it to load. I'm sorry, guys. And I don't think I can pause recording. No, I can't. Look at that battery percentage, though, guys. You guys should be proud of me. 44%, that's a ton. Should be coming up pretty quick. Thanks for your patience. If you look back at the problem, we're going to end up with 13.9. I can just write right here, actually. So we had 13.9 grams of CaO. Now, the second part of the problem says, what is the, there we go. See, I knew it'd come back soon. All right. Let's see where we are. Uh-oh, we lost some of our work. That's okay, though. We can fill it back in. So it was 56 grams of CaO, which gave us 13.888 grams of CaO, and we rounded that to 13.9 grams of CaO. Now, the rest of this problem says, what is the percent yield? So if we look at percent yield, here's your equation up here. It says the percent yield is the actual divided by the theoretical times 100. Now, The actual is always given in the problem, and the theoretical is what you get from doing math. So our theoretical yield is right here. In theory, we should get 13.9 grams of CaO when we do this chemical reaction right here. But it says, what is the percent yield if you actually get 13.1 grams? So we're going to take the actual, which is 13.1. So 13.1 grams CaO, that's the actual, over the theoretical, which we just calculated, of 13.9. 13.9 grams of CaO times 100, and that gives us our percent yield. So I'm grabbing my calculator and I'm going to go 13.1 divided by 13.9 equals times 100, and that gives me 94.2%. So if we look back at this problem, it said, what is the theoretical yield? My theoretical yield is right here. It's in theory, I can make that much. And then the other question in the problem is, what is the percent yield? And remember, I just used this equation up here. What is the percent yield? Right here is the answer to that. So these are the very last problems that I'm asking you to do, and it's the last problems of this chapter. So we will be done with stoichiometry and limiting reagents and all this stuff in a minute. Well, not a minute, like a couple weeks, but whatever. This week, I'm asking you to do number 1, and then I'm asking you to do all of the parts of number 1. So write the balanced chemical equation. You got to write it out. We practiced that last week. This one is just a limiting reagent stoichiometry problem because there's 2 numbers given. So you do 2 problems. Then it says, what's the limiting reagent? Remember, for this one, you just go back to the beginning to see what you started with, and that's your limiting reagent. So this one right here, C, you're literally just looking for the answer. How many grams of copper nitrate can be formed? Copper 1 nitrate. Okay, so this one, you're just going to do this problem. How many grams can you make? You're going to have to look at these given amounts and do that. And then E, how much excess is left over? So take your limiting reagent, start with your limiting reagent, like how much you actually made, your theoretical yield, and then go back to, it's asking you how much is in excess. So go back to your 15 grams of copper chloride and your 20 grams of sodium nitrate, and then subtract your totals from how much you were given. And then this last one right here is your percent yield formula, and this is just a percent yield problem. So number 1 is kind of long, that's why I only assigned you 1 problem. I'm going to erase all the marks I made on here so you guys have a ton of room to work. And if you need help, shoot me an email. We can set up a Zoom video or whatever works for you. Or I can do another practice for you, or tell you where to start, or whatever you need to get these problems done. But like I said, this week I only need you to do number 1 right here, A, B, C, D, E, and F. Okay, have a good night. Sorry about the technical difficulties on this video. Hang in there, we are almost done.